Welcome back. So now I think it's a good time to try to do something with the software we have in order to try to assemble a circuit. So let's do something in practice. So I put this back. And let's try first to verify we have a folder like this one, wherever you want to have it, so which is the material of the course, which contains these subfolders, the Arduino, some documents, Kicad, and processing. So let's start having a look of what we have here. So in the Arduino we have a couple of things. We have project books. So this kit you have came also with a book, which is the one containing all the projects that you can do by using the components they provide you. So I put it here in English so you can better read it. Okay, so it's like this. So many things. Welcome to Arduino. You can have an explanation on the breadboard, so if you don't remember or if you could not completely understand what I was saying, you have also an explanation of these things here. Then you see various components, description, the display, so it tells you whatever you have. And also it gives you small experiments that you can try to do by yourself. So here you have also instruction for assembling the circuit on this wooden board, and I just go fast. So it tells you something about the installation, but this thing maybe can be obsolete because you know that the installation of software is never as in the instruction manual. You have experienced this today with this Windows Defender issue. And then it tells you here you have a schematic diagram of the breadboard. So this is what I was telling you. So every 5 rows they are connected like this. You see, these are all connected together, while the long ones are connected like this. Then here you have a very simple example. For instance, this is something that we can try to do. So a simple LED connected through a resistor to the Arduino board. Let's say this is the hello world of Arduino. So in this schematic diagram, it tells you, for instance, to connect the black wire to this minus thing. So this is connected internally with a little bridge that you can find in this envelopes here. You put one terminal here, the other here, so you connect with the terminal of the LED. Then the current flows like this. It goes inside this resistor. So this resistor is gold on the left, so it reads like red, red, brown, which in this color code is 2 2 and 1, which means 22 multiplied 10 to the 1, so 220 ohms. And then this is internally connected to the red one, and the red one is connected to this pad, which is labeled with this 5-volt symbol. So now we are using the internal power supply of Arduino. Arduino has a voltage regulator that takes 5 volts from this, it takes the voltage from this outlet here, and you can connect something between 7 to 12 volts here, for instance the 9-volt battery, and then this microchip here will create 5 volts out of this unregulated voltage source, or the 5 volts, there is a sort of internal switch, can be taken directly from the USB, and so in the end, in those two pins labeled between ground and 5 volts, you have 5 volts. And so you can use it this way. But this is not a real schematic diagram. So this is, they call it circuit illustration. It's very handy. You can probably find it useful. There are also software that use this type of illustration. For instance, Kicad. It's very useful in order to get into this, but in real life nobody uses this representation, but of course they use a representation which is like this one, which is the schematic diagram. So here you have everything as a, let's say, it's usually represented as a standard way. You have the Arduino Uno represented by a rectangle, so the entire board is now a component. These are the pins that you can have access to, and here wires, resistor, the LED. So this is the circuit representing this layout, physical layout. So the tricky part of doing circuits, after somebody, maybe yourself, designed the schematic diagram, is to pass from the schematic diagram to the real life placement of the component. This operation is usually called routing. You have to route a circuit. So you have to try to understand how to transform this topological representation of the schematic view into something which has a physical dimension, like the wires with a certain length and so on, where to put the components. And the same thing happens when you want to build a printed circuit board. So in principle, in the schematic diagram you can put whatever connection you want, the way you want. The only information you have is what is connected to what, but not how. For instance, in printed circuit board we have a very big constraint. The constraint is that we are working in 2 dimensions. So it's a board. This board has 2 layers. The upper layer, so you see the tracks in connecting the various components. There are tracks also on the bottom, and most of the time some boards have internal layers which are not visible, and they are interconnected by means of small holes. I hope that it is possible to see, which are not the big ones here, but are these very, very small holes, which are called the bias holes. Maybe later I can show you these holes better under the microscope. And these are used in order to interconnect internal layers of tracks of copper that are conductors. Okay, so this is the book. You can find many other circuits, very interesting, many things. So if you want to practice, you have also this thing. Then there are a couple of other things. So this pinouts folder in the Arduino folder is also useful if you want to do something with Arduino. So for instance, we have Arduino Uno pinout. So there are, I mean, you can find this kind of very colorful and good looking diagrams if you just Google them, like Arduino pinout, Arduino Uno pinout, you can find them. So what is this? At some point, some years ago, somebody had an idea of representing all the possibilities for connection of an Arduino board in a single diagram. Have you ever seen such kind of diagrams for Arduino? Do any of you have ever seen such kind of?
Not one of these.
Okay, so these are popular. These are called pinout diagram. So what exactly is a pinout? So usually boards are made like this. Let's take this small one for instance. You see, you have many components on them, but you have some pins, specific pins, which are those ones with these big holes, which are the only connection you are supposed to use. You are not supposed to connect things inside the components, but only to this. If you remember, for instance, during the theoretical course, we were speaking about black boxes to represent two-port networks, like boxes with an input and an output. So these are like this, but there are many inputs and many outputs. What are they doing? So the description of what the input and the outputs can do is usually called pinout diagram. So here you have Arduino and all its pins, so the ports you can access to, which are the ones corresponding to the place where you can put a connector or a piece of wire like this one, for instance. Just to be clear, I mean those things, I'm speaking about those things. So this is a connector that I can connect it like this. And here you have a description of the function of those pins. So those boards can be complicated like this one. It's not that one pin do only one function, or let's say not all of them do a single function. For instance, some of them, yes, like this one, for instance, the ground pin only implements the ground function. It's an analog pin. It's on the power section here. The 5-volt pins only provide 5 volts. But for instance, let's say this one, for instance, which is maybe easy to understand. So Arduino can have digital and analog pins. So analog pins means that they have an analog to digital converter attached to it in order to be able to acquire signals. And these are the analog pins from A0 to A5. But those pins can be also programmed to be digital pins in case you need. So it means that there is a sort of switchboard, electronic switchboard inside the Arduino board, and this switchboard is located inside the microcontroller, which is this big chip one you have. So the microcontroller can be programmed via software in order to use its own pins in different ways. And here you have a table according to a color code, which is written here. For instance, you see If you see the black color on a pin, it means it's a ground. If you see red, it's a power pin, like 5 volts. If you see this green color, it's an analog related pin, but if it's gray, it's a digital one. So for instance, if we go here, the pin number A0 can be either analog or digital, having a name. So if you program it as an analog pin via software, then it becomes the analog pin ADC0. If you program it as an input pin, a digital pin, it becomes the pin PC int 8. So this is the name of the pin, and so on. So they share multiple functions. So this is why you need to have such kind of pinout diagram in order to know what you can do with this thing. And now this thing can be a little bit complex, but I'm quite confident that with the time you can navigate this kind of diagrams. So now I close this. There are many things. Also, you have the breadboard pinout again here. And then, for instance, in Arduino, you have a couple of codes, and one here is the code which is the main code we will be using in this course. The other are just other examples. The bioamplifier code, sorry. So you have a .ino example here. Then there is this picture which is showing how to connect the electrodes if you want to measuring your heartbeat. Here is the one that shows how to connect the electrodes if you want to measure the electrical pulses from the bicep muscle. This is what we will do in the course. The other is just for the sake of completeness if you want to try yourself. Then here you have different views of the board as a picture populated with the components. So you can try to assemble this circuit and we can start doing this today, and then I will leave this for you as an exercise, because then we will use this circuit. So one way to do is just to copy what you see in the pictures. So you have pictures from different sides, also at different level of development. For instance, what I suggest you is to first try to put the operational amplifier like this, and be careful of the orientation of the amplifier. Now I will tell you this better. And these bridges, according to the schematic diagram, we will see in a while. And then basically you can see this from here. You have a picture of the components you will need for this circuit. So in this case, what you will need is those resistors. They are all equal in this case, so it's 10 kilo resistors and two 100 microfarad capacitors that you should have in this box. They are those ones, like this one. The 10 kilo ohm trimmer, and then in the end we will use this configuration for the electrodes, and we will explain how it works. Okay, so then I go back, I go in the processing folder. So what we have here is a serial plotter code, which is the code that we need to use in the processing. So this is the log of processing. It's a processing application. This name is very bad. I don't know why they call it processing, because it's very confusing. If you Google something for processing, I mean, this name is misleading. They could have chosen a different name. Anyway, this serial plotter is a sort of software oscilloscope that will communicate via USB with the Arduino board. And in the Arduino board there is another software which makes the Arduino board to become an analog recorder. So something that will record signals. It will acquire signals, we will see how, and then it will transmit via USB to your computer, where you have this other software that will plot the signals and save them as a txt file that you can later analyze in MATLAB or whatever. So at the beginning of this course, actually during in the email I sent you, I was suggesting to install all this on a laptop for two reasons. One reason is that a laptop can run on batteries. So if you unplug the power cord, it will run on batteries. And this is an advantage because usually when you have something that runs not on batteries but it's connected to the mains, it picks up a lot of noise. So this circuit is, let's say, the best I could do within this small breadboard and those components in order to amplify biological signal, which is very weak. So it's not, let's say, exactly a bioamplifier signal that you can find commercially, but it's the minimum thing that can show you how it works. And it's very connected to what we have done in the theoretical part of this course. So it's simple enough and good enough to do something. And so for this it's better if you have this software connected on a laptop. The second reason is a reason of safety. So it's extremely unlikely that you will hurt yourself with this circuit, because it's all low voltage and it's not creating voltage but it's only measuring voltages. But just to be compliant with the safety rules, it's not a bad idea to have something connected to your body which runs on battery. So it's a bad idea to have something directly connected to the mains, like 220 volts, then is transformed into 12 volts or whatever, because let's say just in case of extreme danger, like your computer is exploding, whatever, you drop a glass of water on the keyboard and then you create an immense damage. So if you have the computer disconnected from the 220 volts, then there is absolutely zero possibility that you can get an electric shock. You can be hurt by this, because with this low voltage contained in a battery of the computer, is basically impossible to hurt yourself. So for these two reasons, I suggest you to use a laptop when you want to do this kind of experiments in complete safety. And then, so what we have here is the last thing is the, let's say, the Kicad folder. Okay. So here we have a couple of projects. So let's concentrate on this bioamplifier. So if you open this folder, you have a bunch of files. And now what we want to do is to open this file, bioamplifier.pro, stands for projects. So you can go here and you can double click it, and that should presents you this Kicad project. So I ask you to do this and to open this project on your PC, so you have it. So once you see this, you tell me, and then we can continue.
Okay.
Could you open the project?
Yeah, it seems like everyone.
Okay.
So everyone? Yeah. Okay.
So everyone is ready? Okay. Is there anybody that could not open the project? Fine. Okay, so
Yes.
thanks. So now we can continue with this description. So what you have here is this view of this CAD, which is very popular nowadays, and it became very solid with the time. It's developed by the CERN laboratory in Switzerland, and it's maintained, it's open source, and it's a professional software. They use it at CERN in order to develop all the electronics for this wonderful particle physics experiments. So you can use it professionally, even if it is open source. I mean, even if it is free. So I think it's good, and it's always updated. And let's say because it's used at that level, it's also a good warranty from the point of view that if you start investing your time studying this, then it will be present for many years to come, because the worst thing that you can do during these days is to be attached to something that you waste a lot of time to studying, and then it disappear because of this vaporware software that sometimes you have, or maybe you start learning something and after 2 years then they put you a fee of €1,000 per month, or 100 or whatever, that you have to pay in order to continue using. But this one is quite good from this point of view, and professional at the same time. So here you have a number of icons, which are small applications. The one we will use mostly, let's say maybe only, is the Schematic Editor. So this corresponds to this bioamplifier kicad.sh file. So if you double click it, it will open this Schematic Editor application, and then we can start having a look of this thing, this circuit. So now I try to zoom out in order to have a panoramic view. So what we have here is a toolbar with common tools like a magnifying lens and whatever, plus other things. Then we have another toolbar on the right with some tools. For instance, you have these triangle things that resemble an operational amplifier. Is the add symbol tool. So if you go here, you can add a symbol in your schematic diagram. I just show you. So if I click it, then it will open this thing. It will load all possible schematic symbols from a diagram. Okay. Now,
can you tell this one again?
Yes, okay. Now, before doing it again, I have to click an option that occurs only at the first time because I installed a fresh copy of Kicad just a couple of days ago on this computer. And if it pop-ups to you, I suggest you to select this pre-selected option, recommended, and click OK. And now I do it again. So now it is probably doing something. So I click this. Now the computer is thinking. Let's wait. Let's see what happens. Okay, nothing happens. Okay. Schematic Editor not responding. Good. So okay, now it did what it was supposed to do. So the first time it probably has to install something. It takes a while. So now I try to fulfill your your question. So I do it again. So I go here in this add symbol icon, I click it, and then this is presenting me a window from which I can select components. For instance, if I scroll down, I can find this device library, and from this device library I can select many things that I can put on my component, on my schematic diagram. For instance, a battery, C is a capacitor, or whatever, many components. So diodes, all these D are different type of diodes. So now I scroll down, LEDs, microphones, an oscilloscope you can put. So now I try to go here where I find something simple like a resistor. So it shows me the type of symbol, and then if I click OK, then I have this symbol here and I can place it where I want. Now I put it here. And that's it. So here I have it. So then you have the contextual menu, which is the right click. So you go on the component, you right click it, you can move, you can drag, you can rotate, you can mirror it, you can do a number of things. So one thing that is important to know in this all these schematic diagrams, the components usually have at least two fields for the description. So you see R, and then there is R question mark. Let's go at this one, for instance. So you see this resistor is called R1. So that is the name of that component, the so-called part number. This capacitor is called C1. Then we have another capacitor, but it's C2, it's another capacitor. So the part number, which is also called designator in this nomenclature of schematics, is telling you which is which one. The other label is for the value. So this is a resistor. The resistor has only one value, which is its resistance. It's not like this for the capacitors, for instance, because we have already met those type of electrolytic capacitance. They have two values. They have the value of the capacitance in microfarads and the value of the voltage, the maximum voltage. So for instance, if I right click this component and I go to properties, then a panel appears showing me different things. For instance, the reference name C1, the value, and other things that I can add. For instance, I could add a field. I didn't do this because it's not interesting in our case. And in place of value, I can put, for instance, voltage, like operating voltage or maximum voltage, and I can add many values. Now here, some of them are shown, some of them are not. You can decide whether to show all these values on the schematic diagram or not. For instance, why you want to hide all possible values of a component, because some components can have too many values and then the schematic diagram becomes crowded and then it becomes unreadable. So you can decide to appear or to make appear or disappear in different layers of information. So another thing which is useful to understand is the colors. So yes,
Can I ask you a question? How can you see the properties of the element? If I try to...
You right click it. For instance, now I'm right clicking this operational amplifier, and then you go down to properties and you click properties, and then you have this pop-up window. You want to do me to do it again, so we take another component, for instance this resistor R1. I try to zoom it. So you right click it and then you go down to properties, and then a panel will appear.
Yeah.
Okay. So about the colors, in this CAD, computer-aided design, the components are usually marked in red. Some of them are filled in yellow, like this one. The conductors, so let's say the wires, are marked in green, and the blue things are just text. So for instance, those boundaries I put in these dashed lines are not electric wires, so these are not electrical connection. These are just groups of components. I mean, it's just comments, so it's for us. It's not doing anything in this schematic diagram. For instance, if we want to have a look of this, here there is a sinusoidal generator, which will be, let's say, a representation of a signal from our neuron. I call this V neuron. So these things, for instance, has a number of properties expressed here in this purple text, and I enclosed it in a cage. I enable in a box I label neuron. So we can see different part of the circuits this way, and so we will comment this schematic more carefully. Then there is another thing which is interesting to know. So you can use this tool . on the right to add a wire. So you have now this wire tool. I can click in a point and then I can start drawing tracks to connect things together. And I finish this command here, and this arrow is for selecting. So let's say the three main things is the arrow for selecting things, is this add symbol and add wire. Then now I go back. Now I take this resistor I put, for instance, I can rotate it like this, or I can select it like this by drag and dropping something, and then I can move it, and put it wherever I want. So let's try just to make a connection like this. I mean, this would be a very easy connection. I'm just short-circuiting this resistor, but just to see how it works. Then I take this, then I don't want to have this, so I select it, I right-click everything, and then I delete this. Okay, so don't be worried to modify the circuit, because even if you destroy everything, you can always re-download the zip file from the GitHub repository. So, or in case, just make a copy of the folder, like i2e main dash my secret copy, and then in case you destroy something, you can just, I mean, it's easy if you restart from the beginning if you don't know how to undo the things. There is also, of course, an undo command that you can use as usual in many software here. So edit, undo, Ctrl Z will do its job. Okay, so these are the main things. Then we have to understand another thing, which is interesting, we will use during this course. So under the menu, let me check what it is, inspect, we have this icon, simulator. So this thing will open another program, which is this one. It's called Spice Simulator. So I never remember what spice means, but maybe this is the good time to try understanding this acronym. If you just Google for spice, I do it on this other computer. Let me see. Too many windows I have here. Google Chrome. Spice Simulator. Spice. Okay, let's see what Wikipedia says. Okay, Spice, simulation program with integrated circuit emphasis. This is what it means. Never mind, it's just a simulator which is based on some models that you have to have, otherwise it can't simulate anything. So if I minimize this and also this, and you go, and if I go here in the folder where I put the components, so what you can see is that there are a couple of files. For instance, there is this TL084, which is our operation amplifier .lib. It's a library file. If I open it, then this text file looks like this. So it's a human readable file, so you can read. It's not a binary file. It tells you what it is, and then it starts with a number of things like this. So what are those things? So those things in the electronic jargon, it's a netlist. So it is telling you what is connected to what inside this component. So if we Google again for this, now I can't click this thing, let me see if we can do with this. Okay, if we go back to this thing, the datasheet of the TL084, and we scroll it up till we find this. This is the internal schematic diagram of the amplifier. So this amplifier is made of a bunch of transistors, resistors, then there are...
Sorry to interrupt you, we can't see what you are actually, like the diagram that you are talking about and the thing. We can only see the sketch that is from the bioamplifier schematic.
So you can't see the iPad now?
We are seeing this, but before you were talking about library, you were telling us, yeah, yes. Okay, now we can see.
Okay, sorry. So I go back. So if I go to the folder, bioamplifier folder, there is a file here. It's called TL084lib. If you double click it, then you have it here. So it's like this. So you have a description in this SPICE language, which is called the netlist, which is all this thing. And this thing is a representation of this other thing, which is the internal schematic diagram of that component. So that file, that lib file, has been produced previously from the manufacturer by means of another CAD computer, like similar to sorry, to Kicad, and it is the so-called SPICE diagram of or SPICE library of the component of interest. So you have to have that file in order to simulate it. So where can you find that file? You have to Google it and try to find it on internet. Sometimes you find it at the manufacturer web page. Sometimes you can't find it that easily, so you have to try to find it. So let's try to find it. For instance, if I do like this and I Google for TL084 SPICE model is the keyword. Then, for instance, here we have TL084 spice model in datasheet. Let's see if we can find it from here. Here it's not possible to have it, so let's try to find it from another location, maybe from here. Okay, part number. It's not always easy to find it, so this is why I put it in the folder. Let's see what we have if I do this. Okay, product details. Package pins feature description maybe. Let's find it from another place. Let's see, what is this? Okay, here it is. This is the file. So you see how in practice this thing is not as easy as it might be. It is similar, let's say, if you are in science, you want to say, okay, a question like where can I find good papers, good scientific papers? It's not so straightforward. One can say, okay, read them from nature, simple answer. But nature maybe is not publishing the papers you're looking for, or who is the best scientist that produce high quality papers. You have to be into that environment. You have to know something maybe that your mentor tells you, or maybe you have to read and then you can understand that, okay, this is good. Then you follow the references, you find other papers, maybe you go to meetings, to the journal clubs, or to conferences, you talk with people. So it's something like this also in electronics, so it's not different. It's something that you can develop with the time. Okay, so now that we have this spice model, what we can do is to use it. Now I show you just a glimpse of this. So I close. No, let's put it here. Let's leave it like this here. Now we go back to Kicad. Okay, here we are. So I just want to show you that once you have the spice model for every component you need, if we right click the component in the schematic diagram and we go to properties, then we can find a button spice model, and with this button we can load this text file, the spice model for the component. So now this model is a quad model because the real chip contains 4 operational amplifiers, but it's including this TL084.lib spice model that we have downloaded from internet. So by telling this to the CAD, to the schematic diagram, now the schematic diagram knows there is a physical component attached on those pins, like VCC 1 in plus 2 in minus, 2 out, 3 out. Those labels are labels which are mapped onto this pinout of the components. So you see this triangle shape of the operational amplifier is a black box with 2 inputs and 1 output, and they have a number. These are the number of the pins, exactly as we have seen in the pinout of the Arduino. So let's say the properties of the components usually are the designator, which is a label which is telling you which is the instance of this component you have in the schematic. For instance, this one is U1D, and there is also U1A, U1C, and U1B also as well, because this operational amplifier is a quadruple operation amplifier, so this microchip has 4 of them inside, A, B, C, and D. And so the nomenclature in this case is that this is U1, A, B, C, and D. Then the label that tells you what it is, a symbol that represents it, and the pin numbering that tells you what are connected to what, and eventually, if you need it, a spice model that will allow you to simulate it. Okay. One other important thing is to notice that such kind of components like this one are kind of symmetric. So how do you know you have to mount it on the breadboard like this or like that? For the microchips, they have a notch that you can see here. So can you see this notch? There is also a kind of depression here, like this little circle. Let me see if I can show you better. Here, sorry, here. But the notch of the microchip usually has this shape. It's okay, now you see it better. And speaking about this thing, so this thing is there in order to tell you where is the pin number 1 of the microchip. So when you see the notch and you have it oriented like this on the left, the first pin here at the bottom is number 1, then this is number 2, 3, 4, 5, 6, 7, and then you proceed counting like this: 8, 9, 11, 12 to 14. So you count them like this in a U shape. So 1, 2, 3, 4, 5, 7, and then you go around 8 till 14. So for instance, just to say it better, let's say we want to connect this thing to resistor R2. We have to identify the microchip TL084, this one. We have to identify pin number 1, 2 and 3. So here is the notch, 1, 2 and 3, and then we connect the pin number 1 by means of a wire, for instance, which is this wire, this one, to resistor R4, for instance, which is 10 kilo. So if we do something like this, then in real life it will be, we place the component here, for instance, then press it so it goes in. Then we can say I want to connect a resistor of 10 kilo like this one, according to the color code. to the pin number 1 at one side, and at the other one, for instance, let's leave it open. So now this thing you see here is implementing this connection here between this resistor and this pin of the component. So this is what it's doing. The resistor doesn't have a polarity, so you can flip it like this. The microchip do have a, let's say, a polarity. It's called polarity in the sense that you cannot reverse it, otherwise you completely misconnect all the connections because you flip it. Diodes like this one, which is not used in this case, they do have a polarity, the anode and the cathode. Capacitors do not have a polarity unless they are polarized capacitors, like the electrolytic capacitors, and you see they have a polarity because there is a minus, sometimes a plus on the other side, indicating the negative part of the capacitor. So what is the polarity of a capacitor? So big capacitors are constructed by creating a layer of oxide by electrolysis, not actually electrolysis, electrochemical processes that occurs in the factory, while they put a voltage which is bigger than the maximum voltage written here on the capacitors, and they create a layer of oxide which completely surround a metal, which is a sort of stripe in this kind of cylindrical capacitor, wrapped in a spiral way in order to fit it in this small space. And these are the plates of the capacitors, and the plates of the capacitors are made of very porous metal in order to have a higher let's say equivalent surface. And then this layer of oxide is created by this electrochemical processes, applying a voltage here, and this is an insulator, and it's a very thin layer. So if you remember, the capacitance of a capacitor is inversely proportional to the distance of the plates. So if you put two plates very close each other like this, and in the middle you have an insulator, which is this layer of oxide, then the capacitance can be very high. So one layer of one plate is the metal plate, and the other plate is an electrolyte. In principle, something similar to this conductive gel. And the insulator is this oxide layer. So this can be created only according to some electrochemistry, and if you reverse the voltage, this layer is destroyed. So for this, those capacitors have a polarity, which is also indicated in the diagram here. So this symbol is the symbol of polarized capacitors. These are the two bars. The black one, sorry, not black one, I mean dark one, is the negative pole. The one close to the plus is the positive pole. So just to be more clear, for the capacitor you have in this breadboard for the circuit, this is the capacitor we will use. So you see the negative side is clearly marked with this minus, and the other one of course is the positive. So here this capacitor goes like this. The negative goes to this. This one is connected like this. So we have to be careful how we connect these capacitors. Other things that you might need as a generic information is, for instance, you see there is in this quadruple amplifier, there is a fifth part which is seen as a component in the CAD, which are the two pins for the power supply of the chip. So we have to remember that an amplifier is something that amplifies a signal, but the power of this amplification is taken from the battery, which is connected to it. And so we have to provide power to the microchip. So this diagram is telling us that this power is provided in this microchip at pins 4 and 11. So 4 is connected to the V+, which then is connected to the 5 volts of Arduino, which is this power port we see here, the 5 volt, while the 11 pin is connected to V-, which is connected to this symbol, which is the symbol of ground, which means the negative pole of the battery, our 0, let's say, which is ground. So in the end of the story, no matter how we decide to route the circuit with how many wires we want, those two things has to go there in order to have the microchip powered up and functional to be used. So here we have extra symbols of components which are not exactly present in the circuit. This is a voltage source. So this is the symbol of the voltage source, which represents the fact that we are taking a voltage from this source, the ground and plus 5 volts of Arduino. And in this case I also added in series to this another source of voltage, which is this noisy thing, because we will take advantage of the simulator also to try to simulate the presence of noise, so we can try to understand how the circuit will behave in presence of noise before assembling it. And this is very useful if you want to study the behavior of your circuit in a controlled way. So now in this circuit we have noise, of course, noise is everywhere, but how much noise we don't know. So how can we know if this circuit will work if we did our design carefully in order to handle this situation of noise? We can try to add noise via software and see what happens, if this design is robust enough to reject this noise or not. Similarly here in this section I put another source of noise I called external noise, which is different from this noise. This noise is a noise that I simulate as embedded in the power supply. You remember I told you that if you have a laptop and you disconnect it from the mains, it's better because you have less noise. I'm talking about this noise here, a voltage noise. So the voltage is not perfectly stable, but it can have some fluctuation, the power supply. But similarly, when I want to amplify the voltage of a neuron, and here we have a voltage source representing our neuron, so this ideal signal is superposed by external noise coming from radiation. For instance, you can have a Wi-Fi or a mobile phones or whatever other sources, and this is now simulated as an external noise which is injecting currents by means of these two resistors, which I labeled as R noise 1 and R noise 2, and they go adding a signal where we don't want to have it, so on the neuron. The neuron is connected by means of two electrodes. Now I put two electrodes having both 1 megohm of resistance. We can try to change the value of this and see what happens. Then there is a piece of wire which is a physical line. So there is some physical space between the neurons we have in the hand or in the arm attached with the electrodes. If I put my electrodes here, and the location of the circuit. So I'm speaking about those long wires here, the ones that goes to the patch electrodes, and on the other side to the amplifier. So this thing is like an antenna. It can pick up noise, and this will be detrimental to our signal. So I just underline the fact that this connection that in this schematic diagram is just topological. It means that it's just a netlist. This node here connected to this node, in fact, they have a meaning for us. So noise can be picked up by this line, and this is exactly represented by these other two things connected here. So the noise in our system will enter from here, from the schematic point of view. Then those two inputs goes one here to the pin number 12, the plus input, and the other plus input of those two operational amplifier, which are implementing a so-called 3 op-amp amplifier, also called instrumentation operational amplifier, which is something we have seen during the course. So we have a first stage made of 2 amplifiers. They amplify the signal according to a gain which is set by this black box, which is called the feedback network. We will see this into details. And once the signal is amplified, we want to get rid of the noise by making a differential amplifiers, which is the second stage here. So if you remember, if you have 2 electrodes having the same type of noise superposed, if you take the difference of the voltage between those 2 electrodes on the assumption that the noise is the same, you will cancel out the noise. So this is the beauty of having the differential amplifier. So what can try to guarantee this condition in our case? The fact that the wires we are using are very close each other. So you see they spread apart in different region of space only where we have them connected to the alligator clamps that then goes to the patch electrode. So actually this part is the most sensitive part from the point of view of picking up noise in our system. So most of the noise will be picked up by these loops, intrinsic loop that will be formed by the location of the electrodes. This thing is kind of compensated because if there is a noise in the proximity of one of the wires are so close each other that maybe the noise on the other wires adjacent to this is kind of the same, and then it will be subtracted. So this is why it's important to carefully think about the location of the wires when we want to do these kind of things. And why it's important? Because we are trying to amplify a signal which is very weak and with a very high input impedance amplifier. Because if you remember, the input impedance of an operational amplifier is very high. Let's say it tends to become infinitive. It's not infinitive, of course, but it can be easily something like 10 gigaohms. So if you remember the trick I did by measuring the resistor and touching this with my hands, an impedance of a resistor of about 10 kilohms was already subjected by putting 300 or 500 kilohms in parallel to this. So something like 10 gigohms, it's a very, very high sensitive input. So everything that is there can stimulate this amplifier to amplify the signal at the output. So we have to take care of this. Okay, so let's say another couple of things about this circuit. So we said that it is composed of a neuron, of a part that is taking into account the presence of the electrodes, this differential input where external noise can enter, a 3 op-amp instrumentation amplifier whose gain is set by this feedback network we will analyze more carefully, and the differential amplifier, which is just taking the difference of what is present here and creating the corresponding output at the with this noise cancellation. There is another amplifier here which in principle is not needed, but it is needed in these schematics because of one fact. The power supply of an operational amplifier is dual, so it needs a positive and a negative power supply respect to a ground in order to being able to amplify both the positive and negative part of a signal of an oscillation, let's say. So we don't have such a dual power supply, which basically means that we need to have 2 batteries here connected in series, but we have only 5 volts. So we need to find a way of having 2 voltages, one positive and one negative, respect to the ground. So what we have here is a circuit which is usually called a virtual ground, which is an amplifier that takes a reference voltage obtained by a voltage divider made by 2 resistors, now implemented by a potentiometer, or also called trimmer. I'm speaking about this thing here. So this trimmer is connected with one pin at 5 volts, the other one at ground, and the slider is connected at an intermediate point that you can move by turning the center of this thing with a screwdriver, or you have this handy knob in your kit, and you can set this in order to pick up half of the value of the resistance. So this resistor will become something like 2 resistors in series, and you take the middle point of them, and once those 2 resistors are equal, then this thing is getting exactly half of this voltage here, and this comes from the solution of this voltage divider. We can do this later as a simple calculation. So the purpose of this is to have 2.5 volts here as a reference. These are amplified by this amplifier in a so-called buffer configuration, which means that the gain of this thing is 1, and we can see this into better detail. And here what you have is again 2.5 volts, but now the current is amplified, and so this can be able to power up, let's say strongly, the rest of the circuits at 2.5 volts. So what we have here now is that these 2.5 volts are connected to this point, which in the schematic diagram of an instrumentation 3 op-amp amplifier would be what we call ground. Now we have 2.5. The negative is connected to 0 and the positive is connected to plus 5 volts. So the situation is this one. Okay, we can also leave this here, but let's put another thing. Oops. So let's draw one amplifier. We said it has two inputs and two other leads for powering it up and an output. So ideally what we should have is something like this. A battery we call plus VCC, another battery we call this point minus VCC, and we call this point G and D. And we connect this to plus VCC and this to minus VCC. But because we don't have those two batteries, but we have only one battery in our Arduino, so we do this trick. We have our Arduino, let's say, with G and D and plus 5. Then we connect those two ports in principle to this voltage divider that creates here 2.5 volts, simplifying the circuits, and we have this thing here, and this is plus 5 volts and this is 0 volts. And then what we do is that we connect this here and this here, and this we label it as ground. So from this point here we have 2.5 volts, and from this point to this one we have other 2.5 volts. So this thing is like having a battery like this and a battery like this of 2.5 volts in series with 2.5 volts, and the middle is our reference virtual ground. It's called virtual just because this is what is called ground in the circuit, but we know that we can set our 0 to whatever reference we want. The only things that are important is the difference of voltages between points in the circuit, not the absolute voltage, let's say. Okay,